In section 6.4, we look at an important class of calculations called mole to mass conversions. And an important idea that we're going to introduce is the concept of a mole ratio. So if I look at a formula like this one here, H2O, what this is telling me is a bunch of information, and interesting information. It's telling me that for every 1 mole of water molecules, I get 2 moles of hydrogen atoms, because there's a 2 in the formula there. I also know that for every 2 moles of hydrogen atoms, that there is 1 mole of oxygen atoms. And I can make a whole bunch of mole ratios of this type for a given formula. And they're going to be really helpful. We're going to use these guys as conversion factors. I can do a similar thing if I have a balanced chemical reaction. If I have a balanced chemical reaction, I can establish these mole ratios between the various species that are present. So if I have methane being reacted with oxygen to form carbon dioxide and water, I know that I make 2 moles of H2O for every 1 mole of methane reacted. Or I could say that I consume 2 moles of O2 for every 1 mole of CO2 that I make. Where I'm getting the numbers from that go into these mole ratios is from the coefficients that appear in my balanced equation. So we're going to kind of like take advantage of both of these types of mole ratios, those that we can establish for the atoms that are within a chemical formula, and also those that we can establish from a balanced chemical equation. So we've already talked about how molar mass functions as a conversion factor between mass and moles. And we gave a couple of example problems. We gave this one here where we said how many moles are there, and we pointed out that it's moles of water that we're talking about here, in 2.5 grams of water. So knowing that molar mass functions as the conversion factor in this case, I'm going to go ahead and calculate the molar mass. I've got 2 hydrogen atoms and 1 oxygen atom, and there it is. You'll probably memorize this before too long. 18.02 grams of water per 1 mole of water. There we are. And so now, to convert from grams to moles, I've just got to multiply by 1 on the molar mass. My grams will cancel out, leaves me with moles. And we saw that exact calculation previously. Now we're going to kind of step it up a little bit. We're going to ask how many moles of hydrogen atoms are present in 2.54 grams of methane. So I know that to convert between grams and moles, I need the molar mass. So what I'm going to do is go ahead and calculate the molar mass of methane. So I've got 4 hydrogen atoms and 1 carbon atom. So I add those masses together and I determine that the molar mass of methane is 6.05 grams of methane for every 1 mole of methane. So my first conversion here, I'm going to go from grams of methane to moles of methane by multiplying by 1 on the molar mass of methane. And that will leave me with moles of methane. And then now I'm going to turn that into moles of hydrogen by using my mole ratio that I was talking about before. And what I'm going to do here is I recognize that I get 4 moles of hydrogen for every 1 whole mole of methane. And that'll convert me where I want to be, which is through to my moles of hydrogen. Okay, so my pathway here was from grams of methane to moles of methane, and then onto moles of hydrogen. It's slightly more complicated because we've included that that mole ratio in the calculation. Okay, so if you have a mole ratio that describes the relationship between reactants and products, and you also know the formulas of those reactants and products so you can get their molar masses, you can figure out how many grams of a product you can make if you're given the moles of the reactant. So this is often referred to as moles of A to grams of B. So moles of one thing, converting it to grams of another thing. So here's a good example. We're going to use that combustion of methane reaction again. It says if 2 moles of methane is reacted with O2, how many grams of water is produced? So I want to convert moles of one thing into grams of another thing. So we call this moles of A to grams of B. And it's not too bad. It's going to be very similar to what I was doing previously, except for we're going to be using coefficients that are in our balanced equation to construct our mole ratio rather than the subscripts that are within a formula. So to get the mass of water, which is what I'm looking for, I take my moles of methane and I'm going to turn that into moles of water by multiplying by the mole ratio. And you can see here I get 2 moles of water for every 1 mole of methane. So that turns my moles of methane into moles of water. And then now I'm going to multiply by my molar mass of water. Remember I said we we're going to commit this to memory, 18.02 grams per mole. And that'll give me my grams of water. This was 2 sig figs, so my answer here is 2 significant figures because my mole ratio is an exact number. Okay, so it's not a lot different from what we were doing in the previous example, except for our mole ratio is based on the stoichiometric coefficients from our balanced equation. Okay, so this is a little flowchart illustrating what we did in both of those examples where we were doing moles of A to grams of B. So what we're going to do is to go from moles of A to moles of B, we multiply it by the conversion factor that has the coefficient of the B on the top line and the coefficient of the A on the bottom line. The mole ratio that relates A and B could be derived from formula subscripts, could be derived from the coefficients that appear out the front of the substance in a balanced chemical equation. Once I've got my moles of substance B, I multiply by its molar mass, and that gives me the grams of that substance. So these are really easy to do. You can sort of recognize the type of problem and multiply by these 2 conversion factors. It's always done the same way. Multiply by the appropriate mole ratio and then multiply by the appropriate molar mass. Okay, a more sort of like slightly confusing approach to this is working backwards, where we're going to be grams of one thing and turn it into moles of another thing. And of course, this could be for 2 reactants, it could be for 2 products, it could be a reactant and a product, it could be going from products to reactants. And in this example, you're going to go from products to reactants. So the question asks, if I would like to make 15.2 grams of Fe2O3, how many moles of oxygen would I need? So I need a balanced equation, and here it is, it's given in the problem. And what I'm really being asked is I've got 15.2 grams of this guy, how many moles of the O2 am I going to need? So what I want to do is I'm going to take my grams of Fe2O3 and then I'm going to multiply that by 1 on its molar mass. And what that'll do is give me the moles of Fe2O3. And you can see that because those units there will cancel out. Now what I'm going to do is apply my mole ratio, and I'm going to get that by looking at the coefficients in my balanced chemical equation. And I can see here that I get 3 moles of O2 for every 2 moles of Fe2O3, and then here's my answer given to 3 significant figures because my starting number had 3 significant figures. So we can go either way, right? We can go from moles of A all the way through to grams of B, but we can also go, begin with grams and work towards moles. So we could do grams of A and work through to moles of B, which is what we did in this example. Okay, so we've learned how to do mole to mass conversions going in both directions, and they always involve two conversion factors, 1 mole ratio and 1 molar mass. If you practice them, you'll recognize that they're all done exactly the same way, and there really are nothing to be scared about. Okay, hope you found the video helpful.